In 1.2, we're going to talk about set builder notation and then some common sets of numbers. So sets that we talk about often, like the set of real numbers, the set of integers, the set of natural numbers, and so forth. So we're going to define those common sets of numbers, and it's going to be important for you to memorize what those common sets of numbers are, because they're going to come up again over and over and over again throughout the course. So let's talk about set builder notation first. Okay. So when describing a set, it's sometimes useful to use set builder notation. Set builder notation usually gives a rule followed by a colon followed by an explanation. We read the colon where. So for example, the set of all numbers of the form n squared where n equals 1, 2, 3, 4, or 5. All right, so this is a set of all n squared where n equals 1, 2, 3, 4, 5. If we wanted to list out the set and give the roster notation for this set, then what we would do is just take turns plugging in these numbers to n squared, right? So 1 squared is 1, 2 squared is 4, 3 squared is 9, 16, 25, and there you go. There's the roster notation. So here's the set builder notation, and here's the roster notation, okay? Let's practice that a little bit more. It says list all of the elements of the following sets. In other words, give the roster notation. Give the roster notation for the following sets. So I'll let you give the video a pause and see if you can do this. Okay, and I'm gonna go ahead and work out my solutions now. There's not really much to work out on part A. On part B, there's maybe a little bit more to do just because, oh, and remember, right? If you square a negative number, you get a positive number, right? Negative 2 squared is negative 2 times negative 2, which is a positive 4. We get 4, 1, 0, 1, 4, but then I'm just going to rewrite this without the repeats. 0, 1, and 4. That's my final answer. Oh, part C is kind of tricky too, because on part C we have 2 moving parts, right? So if I plug in 1, so one possibility is that I plug in 1 for both x and y. Another possibility is that I plug in 1 for x, but 2 for y. Another possibility is that I plug in 1 for x and 4 for y. And then I get the same things, but with 2 in the numerator, right? If I plug in 2 for x. So I could also have 2 over 1, 2 over 2, 2 over 4. I think those are all the possibilities. And I have a feeling I have some repeats here. Because if I simplify these, this is really 1, 1/2, 1/4, 2, 1, and 1/2. So the 1 and the 1/2 are repeats, right? So really, at the end of the day, I would get the set going from smallest to, you don't have to order them from smallest to largest, but I'm just going to order them smallest to largest. I would get 1/4, and then 1/2, and then 1, and then 2. So there's the roster notation. You may think, well, why in the world would we bother with these complicated rules when the roster notation is so much easier? And it's because, well, there are lots of reasons, but mainly it's because whenever we're using set builder notation, it's usually because the roster notation is not easier. It's usually because the roster notation has lots of different elements in it, possibly infinitely many. And so using set builder notation is a way to describe them without having to list all of them off. Let's practice. Number 2 says describe the following sets using set builder notation. So we're starting with roster notation on these, and we're asked to find set builder notation. And I'll tell you, there's more than one way to skin a cat on these problems. So you could come up with a whole bunch of different set builder notations for describing these sets. And as long as it's correct, it's good, right? So in other words, I'm not looking for anything in particular. I'm not looking for some kind of specific answer. But when I look at part A, for example, one of the things that occurs to me is that these are all multiples of 9, right? So I'm kind of thinking of this as like 9 times n, where n starts at -2 and ends at +3. So I think it's the set of all numbers of the form 9n, where n equals -2, -1, 0, 1, 2, or 3. And if you take turns plugging in those numbers, then you see that it generates this set, right? If I plug in -2, I get -18. If I plug in -1, I get -9. If I plug in 0, I get 0, and so forth. But that's just one way to do it. I mean, there are other ways that you could describe this set, but that's one way to do it. When I see part B, well, I'm starting with 1, but I can think of that like 1 over 1. And so what I notice is that the numerators are all 1s, but the denominators are increasing 1, 2, 3, 4, 5, and this keeps going on and on and on forever. So I think what this is looking like is 1 over n, where n is equal to 1, 2, 3, and so forth. We'll have a better way to describe these sets in a second. This set of numbers is called the natural numbers. So, and we're going to talk about that when we talk about common sets of numbers. But anyway, that's a good roster notation for that. Or sorry, a good set builder notation for this roster. Okay, so let's talk about these common sets of numbers. So starting with the natural numbers, as we saw on the previous page, right? The natural numbers are denoted with this n that has like this double stem in the middle, right? But this is the symbol for the natural numbers. Anytime you see this symbol, it means the natural numbers. The natural numbers are the positive whole numbers, right? So the natural numbers are the set 1, 2, 3, 4, 5, 6, 7, on and on and on forever, right? That's the set of natural numbers. So going back to the previous problem real quick, what we could really say, instead of writing this, we could say it's the set 1 over n, where n is a natural number, right? N is an element of the natural numbers, okay? So that would be a better way to write down our answer to number 2, part B. Okay, so that's the natural numbers. The whole numbers are denoted by, well, they're denoted by different things in different texts. I'm going to use a W to represent whole number, but the whole numbers are just the natural numbers, but with 0 thrown into the mix. So you throw in 0, and now suddenly you get the whole numbers. The integers are denoted with a Z. Now, why a Z? To be honest with you, I don't know. I think it has to do with German. Like, I don't know the German word for number or integer or something like, or some, but whatever it is, I'm sure it starts with a Z. so I'm pretty sure it comes from German. Anyway, so the integers are denoted with this Z, and the integers are the positive and negative whole numbers, right? So whereas the natural numbers are just the positive whole numbers, the integers are the positive and negative whole numbers and 0, right? So those are the integers. So in the past, you have probably heard the word integer before, and you probably just thought it was synonymous with number. It's not. There are numbers that are not integers, right? Like there are fractions, there are decimals, right? So there are numbers that are not integers. So integer is not just a synonym for number. Integer means positive or negative whole number, or 0, right? So those are what the integers are. Okay, rational numbers are denoted by a Q. Again, not sure why, probably some German thing, I don't know. But, but rational numbers are denoted with a Q. And rational numbers are the numbers that can be written as fractions. Okay, so this is where set builder notation comes into play, and this is where things start to get a little more confusing. But the rational numbers are the set of all numbers of the form a over b, where a and b are integers, and b is not equal to 0. That's the set of rational numbers. So any fraction is rational. Any integer is a rational number. For example, -3 is a rational number, it's an integer, right? But it's also a rational number because it can be rewritten as a fraction. You can rewrite -3 as -3/1. And since both -3 and 1 are integers, that means -3/1 is a rational number. So -3 is a rational number. Many decimals are also rational. For example, 0.75 is a rational number because you can express 0.75 as a fraction, right? 0.75 is the same thing as 3/4, and 3 and 4 are both integers, right? So 3/4 is a rational number, therefore 0.75 is a rational number. So many decimals are rational numbers as well. Anyway, so in other words, any number that can be rewritten as a ratio of two whole numbers is called a rational number, and that's where the rational numbers get their names. They're ratios of whole numbers. So rational numbers are ratios of whole numbers. Okay, then finally, we've got the real numbers. The real numbers are denoted with an R, and you've probably seen that symbol before in your algebra classes, right? You probably saw it as a stand-in for like all reals. So if you're working on some problem and the solution set was all reals, then the answer in the back of the book might have just been R, right? That's because R stands for the set of all real numbers, right? So the real numbers are the numbers that can be written as decimals. So any decimal number is a real number. Any integer is a real number. For example, 17 is a real number because you can write 17 as 17.0 or whatever. So any integer is a real number. Any fraction is a real number. For example, 2/5 is a real number because you can work out the division. You can do 2 divided by 5 in your calculator or whatever, and you get 0.4, right? You can change this fraction into a decimal. So any number that can be written as a decimal is a real number. Okay, so any number that can be written as a fraction, or in other words, as a ratio of two whole numbers, is a rational number. Any number that can be written as a decimal is a real number. Not all numbers can be written as a decimal, though. You may have seen complex numbers in the past. Complex numbers are numbers that have real and or imaginary parts. So the set of complex numbers is a set of numbers of the form a plus bi, where a and b are real, but I is the square root of -1. And that's the issue there. The square root of -1, you can't write that as a decimal number. It's not a decimal number. It's not a real number. Okay. We call it imaginary. Imaginary is really a bad name for this because it's not any more imaginary than like the number 2. You know what I mean? It's like you've never bumped into 2 in the street. You have no more reason to believe that the number 2 exists as like an entity than you do to believe that the square root of -1 exists as an entity, right? They're all just concepts made up by human brains. So anyway, so there's no reason to think that this is any less real than the number 2. But for historical purposes, right, it's called an imaginary number. That's really a bad name for it, but it is what it is, right? We call them imaginary numbers. Complex numbers are really pretty nice, and we're going to see in this class just how nice complex numbers are when we talk about the fundamental theorem of algebra. But it turns out that the buck stops with the complex numbers. Like there's no need to define any larger set than the complex numbers. Like you might be thinking, well, we define I to be the square root of -1. What about the 4th root of -1? Why don't we define like a number j to be the 4th root of -1 or something like that? And it turns out that you don't need to, because you can describe the 4th root of -1 as a complex number. So the complex numbers encapsulate everything that we need in order to find solutions to polynomial equations and things like that. So this is the largest set. We're not going to define any set larger than that. Okay. One thing that I'll point out is that any real number is complex, right? For example, 2.7 is a complex number because you can rewrite 2.7 as 2.7 plus 0i, right? 2.7 and 0 are both real numbers. So 2.7 plus 0i is a complex number. Well, 0i is just 0, of course. So 2.7 plus 0i is just 2.7, right? So any real number is complex. But not every complex number is real. For example, 2 plus 3i is a complex number, but it's not a real number, right? You can't write I as a decimal, so you can't write 2 plus 3i as a decimal. Okay? So here is the relationship between all of these sets, right? These are they're all kind of nested subsets, right? The smallest set that we've talked about is the natural numbers. These were the positive whole numbers. Then we have the whole numbers. These were the natural numbers plus 0. So the natural numbers are a strict subset of the whole numbers. Then we have the integers. The integers were all the whole numbers, but with the negative numbers, the negative whole numbers thrown into the mix. So the whole numbers are a proper subset of the integers. And then we have the rational numbers. The rational numbers are all the numbers that can be written as fractions. Any integer can be written as a fraction by just putting the integer over 1. So all of the integers are rational numbers. So the integers are a proper subset of the rationals. The rationals are a subset of the reals, right? Because any fraction can be turned into a decimal, and the reals are all of the decimal numbers. So the rationals are a subset of the reals, and then the reals are a subset of the complex, right? Any real number is a complex number because you can just write it as real number plus 0i, right? So you've got this relationship between the sets. Here's an example to help us try to practice this concept a little bit. Ultimately, guys, this is just going to require some memorization, okay? You just have to memorize what these sets of numbers are. Make some flashcards or something. But yeah, you're going to have to memorize what these sets of numbers are. But here's some practice. It says, name the smallest of the common sets listed above to which the following numbers belong. So we want the smallest set. So for example, like all of these numbers are complex numbers, right? So if I had just said, name the set to which these numbers belong, you would just say, oh, this is a complex, and that would be kind of a pointless exercise. So what I'm asking you to do is name the smallest set. And by smallest, I mean the smallest in terms of this hierarchy, right? The smallest of the common sets to which each of the numbers belongs. So 2/3, for example, it's a complex number, but it's also a real number. Is it a rational number? Well, yeah, because it can be written as a fraction. Is it an integer? No, it's not an integer, right? It's not a whole number. So Q is the smallest set to which 2/3 belongs, right? So Q, right, the rationals. So see if you can do this for the rest of these numbers. See if you can name the smallest of the common sets to which these numbers belong. I'm just going to write out my solutions. So here, this one is a whole number. This one is complex. This one is a natural number. This one is an integer. This one is, well, it's a real number, but it's also rational, right? Because 0.5 is just 1/2. This is just 12.5, right? So 12.5, I mean, you could call that 25/2. So this is the same thing. This is the same thing as negative 25/2, right? It can be rewritten as a fraction. So it's a rational number. It's not an integer, so it can't get smaller. It can't go all the way to z, but it can get down to q, right? So this is a rational number. You'll notice that we never used r here. It may lead you to wonder, like, what's the difference exactly between q and r? Like, can every decimal be rewritten as a fraction? Because if so, then these two sets are exactly the same thing, right? Well, that's a concept worth exploring. So let's look. Okay, so what exactly is the difference between q and r? Well, we've said that every fraction can be rewritten as a decimal. So every rational number is a real number. For example, 1/6. Oh goodness, I'm just going to use my calculator. Right, 1/6. 1/6 is like 0.1666666 on and on and on forever. I'm going to write that like this: 1.16 with a bar over the 6 to indicate that the 6 repeats forever and ever and ever. Okay, so that can be rewritten as a decimal, right? So any fraction can be rewritten as a decimal. So Q is definitely a subset of R. But is it also true that R is a subset of Q, right? Can every decimal be rewritten as a fraction? Well, certainly some decimals can be, right? If the decimal terminates, then it can be changed into a fraction pretty easily, right? 3.245, the 0.245 of this is just saying 245 thousandths, right? This is tenths, hundredths, thousandths. So if you keep track of the place value, it's 245 thousandths, which you can just write as a fraction, 245 thousandths, and there you go, right? You could reduce that fraction, and then you could rewrite the mixed number as an improper fraction, right? 3 times 200 is 600. 600 plus 49 is 649, right? So there you go, right? 3.245 can be changed into a fraction. And that's true of any decimal that terminates. If the decimal terminates, if it has a finite number of decimal places, then you can rewrite it as a fraction pretty easily. If the decimal doesn't terminate, but it has a repeating pattern, then it can also be changed into a fraction. For example, to change 2.666666 repeating on and on forever, to change that into a decimal, let x be 0.6 repeating forever. And then note that if x is equal to this, then 10 times x is equal to that, right? You just move the decimal one place over and you get 6.666 whatever. Now, if you subtract these two equations, right? If you do 10x, so if you do this subtraction, 10x minus x is 9x, and 6.6 repeating forever minus 0.6 repeating forever is just going to be 6, right? You get 9x, you get 9x equals 6. Well, so then you can solve for x, right? You can divide by 9. You get x equals 6 over 9, which is equal to 2/3. So, so that means that 0.6 repeating on and on forever is just equal to 2/3. So getting back to the original thing, right, 2.6 repeating on and on forever would just be 2 and 2/3, which can be changed into 8/3. So there you go, right? And you can verify that on your calculator. Type in 8 divided by 3, and you'll get 2.6 repeating on and on forever. So if the decimal terminates, it can be rewritten as a fraction. If the decimal doesn't terminate, but it has a repeating pattern, then it can be changed back into a fraction as well. What if the decimal doesn't terminate and there's no repeating pattern, right? That's the question. And do such numbers even exist? That may seem kind of like a silly question to you, but there was a time when people did not believe in such numbers, okay? Fairly recently, actually, in human history, people didn't believe in such numbers. So it's not like a trivial question, but we can point out numbers that have this property, right? So the fact is that there are real numbers that are not rational numbers, and an example of one of these would be something like the square root of 2. If you plug the square root of 2 into your calculator, square root of 2, then you get this number, and it has a whole bunch of digits. Now my calculator stops at, I think, 10 digits. Your calculator might go further, but this number goes on and on and on forever, and there's no repeating pattern here, okay? So now that doesn't necessarily mean that it can't be rewritten as a fraction. Maybe there's a clever way to do it, right? So let's pretend that there is a way to do it, right? I'm going to prove to you that it can't be done by first assuming that it can be done and then showing that there's a contradiction, okay? So to see that root 2 is not rational, we must show that it can't be written as a fraction. So assume by contradiction that it can be. So in other words, assume that square root of 2 is equal to a over b for some integers a and b, okay? Now, before I go further, these numbers have to be integers. So you might be thinking, oh, well, can't we just write it as square root of 2 over 1? Doesn't that do the trick? And the answer is no, because the square root of 2 is not a whole number, right? So this doesn't work, right? So the question is, can we rewrite square root of 2 in the form a over b, where a and b are whole numbers? Can we do that? So I'm not going to read the proof to you, But it would be worthwhile for you to go through it and see and try to understand the reasoning to convince yourself that in fact, yeah, this can't be done. It can't be done. You can't rewrite square root of 2 as a ratio of two whole numbers. So the fact is that there are real numbers that are not rational. Real numbers that are not rational are called irrational, and we use I to denote those. So the irrational numbers are the set of all real numbers that are not rational. Okay. All right. And it turns out that any number that has a non-repeating, non-terminating decimal expansion is an irrational number. Okay, so the square root of 2 is irrational. In other words, the square root of 2 is in I. In fact, the square root of any non-perfect square is irrational. The cube root of any non-perfect cube is irrational, and so forth. And then there are other types of irrational numbers as well, like Euler's number E, which is about 2.7, or pi, which is about 3.14. These numbers are also irrational. So all of these numbers are irrational. So as I said, the moral of the story is, if the decimal is non-terminating and non-repeating, then it is an irrational number. Otherwise, it's a rational number. So if it has a repeating pattern or if it terminates, then it can be changed into a rational number. So there you go. Not all real numbers are rational. Another thing so a couple things to point out actually. So the real numbers are another way to express the real numbers is that it's the set of all of the rational numbers plus the set of all of the irrational numbers. If you take the union of the rationals and the irrationals, then you get all of the reals. Okay. Another thing to note is that a number is either rational or irrational. It can't be both. Okay, that may seem kind of obvious, but it's worth pointing out. In fact, I doesn't fit very nicely into our hierarchy of sets from the previous page, right? So we have this hierarchy of sets here, and trying to figure out where I fits in is kind of tricky. It doesn't really fit in. It's sort of its own separate thing. Here's a picture. Sometimes a picture is worth 1,000 words. So I'm using circles here to represent the different sets of numbers that we've talked about. So you have the complex numbers, right, which is like all of the numbers. It's like every number. The buck stops at the complex numbers. And then inside the complex numbers, you have some real numbers. And then the real numbers are split between the rationals and the irrationals. Okay? And there's no overlap between those two groups. There's no overlap between the rationals and the irrationals. Okay, and then within the rationals, you've got integers and the natural numbers and whole numbers as well. I didn't feel like putting whole numbers on there, but that's the idea, right? So this sort of represents the different sets of numbers that we've talked about in this section. Okay, let's practice a little bit. This one says, give an example of a rational number that is not an integer. Well, so I'll let you pause the video and see if you can come up with examples of each of these scenarios. So I'll let you work on these. I'm going to give you, I'll give you like 2 or 3 examples of each. So sorry, had to yawn. Okay, so for an example of a rational number that's not an integer, something like 1/2 or -2/3. Or 5.7, right? Those would all be rational numbers that are not integers. Part B asks for an example of a natural number. Okay, so 1 would be a natural number. 7 would be a natural number. 1 billion is a natural number. Okay, something that's not a natural, well, okay, let's do that in part C. Part C asks for an integer that is not a natural number. An integer that's not a natural number would be something like 0 or -14. You couldn't say something like 5. 5 is an integer, but it is a natural number, so it's not an example of an integer that's not a natural number. And then obviously you couldn't say something like 1.6 because 1.6 is not an integer. Okay. Okay, part D. An example of a real number that's not rational. So an irrational, well, we talked about like square root of 2, right? Or pi. Or 2 plus root 3 over 6. Right? These are all irrational numbers. Okay? Very good. By the way, if I'm going too fast, pause the video, rewind the video, rewatch it, right? Part of the beauty of having online class instead of face-to-face class, I mean, there's some advantages and disadvantages, but one of the advantages is that you can pause and rewind and stuff like that, and rewatch. Okay, number 5, list 5 elements of the following sets. Answers are not unique. Yeah, you could come up with all kinds of different answers to these, but I'm going to list off 5 elements of each of these sets. Go ahead and give the video a pause and try it out on your own before you look at my solution. Okay, here I go. So 5 elements of this set. So we have the set 3z where z is an integer. Oh, so this is going to be like, it's going to go on and on and on forever in both directions, but I could plug in like -2 and get -6. I can plug in -1 and get -3. I can plug in 0, 1, 2. There are 5 elements right there. And this is going to continue on and on in both directions, right? Down the negative way and up the positive way. Part B, 1 over n, where n is a natural number. Well, that one does have a definite starting point because the natural numbers start at 1, right? That's the smallest natural number. So if I start at 1, I get 1 over 1. If I plug in 2, I get 1/2, 3, 4, 5. That's going to keep going on and on forever. That's kind of an interesting set, actually, because notice that these numbers are getting smaller the further down the list we go. They're getting closer and closer to 0. An interesting question would be, is 0 in this set? The answer is no, of course, but it's still an interesting question to kind of think about. Okay. Ooh, this is kind of an interesting one. n minus 14, where n is a natural number, intersect n minus 11, where n is a natural number. I'm going to have to do some scratch work here. So I'm going to start. I'm going to start at 1. Since we're dealing with natural numbers, 1 is the smallest natural number, so it seems like a good place to start. If I plug in 1, 1 minus 14 is -13. If I plug in 2, 2 minus 14 is -12, and so forth, right? 11, 10, 9. I don't know how far I'm going to go, but okay, so that's that first set. And then the second set is n minus 11. Again, I'm going to start at 1. If I plug in 1, 1 minus 11 is -10. 2 minus 11 is -9. -8, -7, -6, -5, and so forth. So if I'm talking about the intersection of these two sets, it would be the numbers that they have in common. Well, they don't have -13 in common, or -12 or -11, but they do have -10 in common, and -9 and -8, and every number after that they're going to have in common. So five elements of this set would be like -10, -9, -8, -7, -6. Right? That would be 5 elements of that set. Okay. So that's that. Number 6. Here's a skill that it's like. So here we're supposed to change the following decimals into fractions. This is something that I think we just sort of expect you to know how to do, even though at no point in the curriculum do we ever go over how to do it. So I'm going to show you how to do this. We've actually seen an example already when we were talking about 2.6 repeating forever. We talked about that here, right? This is how you change repeating decimals into fractions. So if you've never seen this before, this is the basic strategy, okay? you let x be the repeating part, and then you do some kind of manipulation where you subtract off the repeating part. Let me just walk you through. Let me walk you through these examples. So we saw one where we just had one number repeating over and over again. Here's one where we have two numbers repeating over and over again. In other words, this is the number 0.12, where both the 1 and the 2 are repeating on and on and on forever. So I'm going to do the same trick that we did before. I'm going to call this thing x. And if that's the case, now if I multiply by 10, that's not going to be good enough. Watch. If I multiply by 10, so if I say 10x, that moves the decimal one place to the right. So I get 1.2121, 2 on and on forever. But if I try to subtract these values now, I'm not going to get rid of this never-ending decimal. I'm going to get like, oh, I'm going to get something nasty, right? So I'm not going to get rid of the never-ending decimal because the digits aren't lining up correctly. So I don't really want to look at 10x in this case. I want to look at 100x. So look at 100x, that's going to move the decimal over twice. So I'm going to get 12.121212. And now notice now, if I subtract these two things, now this non-ending decimal is going to cancel with that non-ending decimal. That's what I want to happen, right? I want to try to eliminate that repeating pattern. So if I subtract 100x equals 12.121212 minus x, which equals 0.121212, then I get 99x equals 12, right? And then I can just divide by 99. And I get x equals, 12 over 99, which reduces. 12 over 99 reduces by 3 to 4 out of 33, I believe. So there you go. We can verify this on our calculator. Let's see. 4 out of 33 is, yep, 0.121212. So there you go. Okay, so hopefully that makes sense, right? The idea is, you let x be the number that you're starting with, and then you multiply by 10 or 100 or 1,000 or whatever you need to do in order to get the repeating pattern to cancel off when you subtract those two values. So that's kind of the idea. Let me show you part B, because sometimes what happens is you have a string of you have a string of digits before you get to your repeating pattern. So this is like the number 0.342, where the 2 repeats over and over again, but the 3, 4 that precedes it never does repeat. So I think we can do kind of a similar kind of trick here. So I'm going to let x be 0.342222. There are probably a bunch of different ways that you could go about doing this, but here's how I'm thinking about it. So first of all, I'm going to multiply by 100 to move the decimal twice so that I kind of clear that 0.34. So 100x would be 100x would be 0. Sorry, 100. I lost my train of thought. 100x would be 34.2222. On and on and on forever. Now, if I subtract these two things, I'm going to have some issues, right, with the 34 here not matching up with the 22 down there. So I think what I'll do now is look at maybe 1,000x, which would be 342.2222, right? And now here, when I do the subtraction, it's going to work out a lot more nicely, right? So I can say 1,000x minus 100x Okay, so 1,000x minus 100x is, of course, 900x 342.2222 minus 34.2222, well, the repeating parts are going to cancel, right? And 342 minus 34 is 308. 308. Okay. Now, the number that I was interested in turning into a decimal was this number, which I called x. So I just need to solve this equation for x now. So divide by 900. So 308 divide by 900. Which reduces by at least 2. Let me see, 308 out of 900 by more than 2. So this will go all the way down to 77 out of 225. So there you go, 77 out of 225. And again, we can verify this on the calculator, right? 77 out of 225 is, yeah, 0.342222. So there you go. So that's how you do that. That's how you change non-terminating decimal back into a fraction. Okay, let's practice rewriting some roster notation in Setbuilder notation now that we have some of our common sets to work with. It says answers are not unique. Yeah, there are lots of ways to describe these sets. So I'll let you work on this on your own, and then I'll give you my solutions. Okay, so here's one possible way. These are just integers, but while they're going on and on forever in the negative direction, they stop at 2 in the positive direction. So I think the way that I would write this is I would say, well, this is the set of all integers where z is less than or equal to 2. Okay, so it's just the set of all integers less than or equal to 2. There are other ways that you could write that. Like you could say, it's the set of all integers where z is strictly less than 3, right? That would be the same set. Okay. Or you could, if you wanted, I guess you could say, it's the set of all numbers of the form z minus 1, right? Where z minus 1 is less than or equal to 2. So in other words, where z is less than or equal to 3, right? I mean, you could come up with all kinds of representations. Here's another one. I'm going to call this n times pi, where n is a whole number, right? If I plug in 0, I get 0. If I plug in 1, I get pi. If I plug in 2, I get 2 pi, 3 pi, 4 pi, right? This one looks like the same thing, except that, right? It looks like n times pi, but in this case, n is allowed to be any integer, right? So n can be negative numbers as well. And then part D, the set of negative rational numbers. Negative rational numbers. Well, I'm going to call this the set of all q in q. I just like it when the letters match. They don't have to. You could call it the set of all x in q if you want. I'm going to call it the set of all q in q where q is negative, right? So where q is less than 0. So that would be that. Okay, so kind of a long section, a lot of material. Last little bit of information. This is optional. This is just what did I call it in the last section? Enrichment. This is just for your enrichment, okay? So for your math enrichment. So if you want to stop watching the video, you can, but you'll be missing out. But you're not going to be tested or quizzed on this kind of stuff. But when we were looking at sets, when we were looking at that hierarchy of sets, you know, natural numbers are a subset of the, you know, whole numbers are a subset of the integers, are a subset of the rationals, and so forth, right? When we were looking at this hierarchy, we kind of used the terminology, we said, well, some sets are bigger than others. But what does that mean exactly, especially when the sets are all infinite in size? Okay. Well, so one way to compare sizes of sets is to say that if B is a subset of A, then A must be bigger than B. And, oh, and I was using the wrong symbol, wasn't I? These should all be subset symbols, not element symbols. Oh, how bad of me. Subsets. They're subsets, not elements. Anyway, but yeah, so one way to compare sizes of sets is to say if one set is a subset of the other, then then it must be smaller than the parent set, right? So we would say n is smaller than w because n is a subset of w. That's what I meant when I said smallest when we were looking at that example. However, this approach has some pretty severe limitations. For example, which set is bigger, 1, 2, 3, or 4, 5? Neither set is a subset of the other. So, so if you're trying to use that criterion to determine which set is bigger than the other, then you have no way of determining which set is bigger. You could maybe say, well, if the set is made up of a set of numbers, you could add up the numbers and see which sum is bigger. In that case, this set would be bigger than that one, since the sum here is 9 and the sum here is 6. On the other hand, you could say, well, you should just look at the number of elements in the set, right? This set has 3 elements in it, and this set has 2 elements in it. So this set is bigger than that one, right? That's the approach that we usually take when we're talking about which sets are bigger than others. The set that's bigger than the other is the one that has the greatest number of elements in it, right? So that's what we do with finite sets, right? So when we have a finite set, like when we're trying to compare 1, 2, 3 versus 4, 5, we say that the set that's bigger is the one that has the most elements in it. So that would be this one in this case. But how do you do this for infinite sets? Like when we're looking at these things, for one thing, there are infinitely many elements in each of these sets that I've listed, and so you can't count them up. For another thing, even if you could count them up, whatever that would mean, they all have an infinite number of elements in them. So what does it mean? Like, how do we compare the sizes of these two sets to each other? It's an interesting question. And it turns out that there is a way to do it. And I have a link here to a video that you can watch to get an answer to this question. This is a super interesting video, in my opinion. This is like one of my favorite things in all of mathematics. So I would strongly encourage you to watch it. I think it's like 6 or 7 minutes long. It's optional, but it's gonna blow your mind. You should definitely watch the video. But basically, it leads to all kinds of cool things about how there are unsolvable problems in mathematics. It leads to all kinds of things about how there are infinitely many different sizes of infinity, right? So really cool stuff, really interesting stuff. Watch the video. I'll post a link to it in the Canvas module as well. But that's that. I'll see you in 1.3.